Multicast. Multicast IP was invented in order to satisfy the things that are illustrated on this slide. Today, TV and radio are either over the air, broadcast mode, or over the internet, and most of the time over the internet it is in on-demand fashion. If you go to YouTube to watch a film, you get a special TCP connection for you, for your session. But you can also distribute TV. For example, if you receive TV from your telecom operator, not from your cable TV operator, you will receive it over the internet using a form which is called multicast. Another, that's not this line, right? It moved autonomously. Another example of multicast is industrial networks, smart grids, or rather industrial networks, where you have devices, sensors that stream measurements to collectors, data sinks, and there may be several data sinks, and instead of having every sensor open a session with each data sink, it sends to a multicast address, and then the multiple data sinks simply listen to the data. Those are the, I would say, the two widespread uses of multicast. So the concept of multicast is that we send to a group, and a group in IP typically means a multicast address, an IP address. A special set of IP addresses. In IPv4, those are those addresses, 224 and above. In IPv6, those are the ones that start with FF00. We've already encountered some of them in IPv6. There's lots of multicast that replace broadcast. In general, so the use of multicast is recognized by the address. Now, a multicast address is a radically different thing than an IP unicast address. So the other addresses in IP are called unicast. A unicast address means it's intended to be, you're intending to reach one machine if you use this address. Note that there can be an IP unicast address allocated to several machines. That's what Google does. Google has 8.8.8.8 as their DNS, one of their DNS name servers, but they have multiple machines that respond to that address. But when you talk to one, when you send a packet to that address, you reach only one machine, one out of several possible, but your session is with one. With multicast, the intention is that you reach several machines. Of course, that completely breaks everything we know about IP. We will see in particular the impacts in routers. The first thing that's obvious that it breaks is that there is no topological information in this. A multicast address is a label of a group. Who is listening to that group? You have no clue by analyzing the address a priori. As we will see, the major difference between unicast and multicast is that the routers need to do considerably more stuff with multicast than with unicast. The job of intermediate systems is more complicated and is different in nature. How does it work? This is perhaps the most important part for us. I'm showing here a very simple network where I have A and B, two potential listeners, and S is the source. So that's the source of a TV program, or your source of if you want to send video or audio at your home, that's your streaming device that sends information. The first thing to notice is that in order to send, a source does nothing special other than specify that the multicast destination address, that the IP destination address is multicast. So there is nothing special to do at the source or as a programmer when you send. You simply, if you use UDP, which you probably do because that's the only thing that works with our multicast, you do send to, and then the address argument of send to happens to be a multicast address. Then, how will thing work? Well, if S sends data, it simply sends to M. If nobody in the world has actively subscribed to this multicast address, that's a terminology that's often used. If nobody is a listener, then the packets will be issued by S and will be dropped by the first router. So S is multicasting to no one, and that can happen. Nothing will happen. There will not be an error message typically sent. S will not be able to know whether someone is listening or not. But hopefully somebody is interested in receiving, for example, A. If A wants to receive, A needs to do something. A needs to send a subscription packet, which for IPv4 is called IGMP, Internet Group Multicast Management Protocol. And as you can imagine, for IPv6 is the same but with a different name. It's called MLD. This host, A, needs to talk to the routers by sending a packet which for IPv4 is broadcast to all routers, for IPv6 is sent to all multicast-capable routers, saying, I would like to receive the data that corresponds to multicast address M. In sockets, this is done by setting a socket option somewhere. You need to instruct your socket that you want on this socket to receive data. Once this is done, what will happen? Well, this will trigger a chain of events in the network, if the network supports multicast, which is the case if you are a customer of Swisscom or Sunrise and you want to receive TV, but this is not the case in all networks. It's the case also on EPFL networks. It's not the case globally on the internet. If you send multicast packets to an arbitrary place in the internet, this might not work. But if this is supported, what will happen is a chain of events that results in those red boxes shown in the routers. The red boxes are not packets. Here they show state information. So the first router, R1 that receives it, will simply remember somebody is listening to M on that interface, on port, the left port here. So R1 will keep a flag somewhere saying not more than a flag, will keep a list of multicast addresses, we'll put M in that list, and the interface, the one at which the join will receive. Then R1 needs to do more. R1 needs to trigger something to create a multicast distribution tree, or to attach to an existing tree, or if there is no existing tree, like in this case, to attach to the source. This is done by several possible ways. The most classical way is to run what is called a multicast routing protocol. The one that runs on EPFL network, for example, is PIM. So if R1 uses PIM, it will send a PIM message to all its router neighbors, or more precisely, using PIM, what it will do in that case here, it will try to establish a tree, a distribution tree, and the simple way to do it is to go to the source. So using the routing table at this router, what it can do is go to the source of M. If in the IGMP message there is indication of the source, which is one of the options, sometimes there is, sometimes not. If there is, then you simply go along the internet towards the source, but at every router on the path, you send a PIM message, which will instruct the router to continue building the tree. If that succeeds, we will have those three routers, R1, R2, R5, that now are on the have built a distribution tree for multicast address M. If there is not the indication of the source here in the multicast message, things are more complicated. There are other options to do it. Multicast routing is not very, very widespread. It's done in those TV distribution networks. It's done on EPFL networks. Other networks use out-of-band mechanism. One of them we will discuss a bit later in 1 or 2 hours is called software-defined networking, where you can go directly from a central location, you can activate this state information in all routers instead of having it in a distributed way. So those two methods exist today. Once this is done, then the next packet sent by S, when it reaches router R5, for example, R5 knows it has to forward it to R2 because it has received from R2 a message, a PIM join message, and R2 has received from R1 a PIM join message. So the routers will do like they do for other unicast packet, they will forward it, and R1 will put it on the local area network where it will be multicast. We have seen how it is multicast in local area networks. It's either broadcast in dumb networks, or the switches will build a distribution tree as well. So that's a very simple case. There's not much multicast. There's only one destination. What happens when a second destination joins, like B? Hopefully you have more than one destination to your multicast group. But notice that even with one destination, multicast is different from unicast. So when B joins, R4 will do the same thing. R4 will, if it's using PIM, it will send a PIM join message towards the source, which in that case is R2, and the thing will be merged at R2. R2 now is already on the distribution tree for M, so what R2 will do is add a second state information or complement its existing state information, saying there are now two interfaces on which I need to send the packet, which means R2 will have the job of duplicating the packet, will have the job of distribution is, as we see, done by routers. So whenever S now sends a packet, as you can imagine, the packet is sent by R5, duplicated by R2, and then independently forwarded by R1 and R4 to the sources. Voilà. This is how multicast works in the internet. That's practically all that we need to see importantly. We have seen that how this is handled at the MAC layer. We have seen that the MAC layer does not use ARP to find what are the IP, the MAC address that we put in multicast packet, and the answer is we put MAC layer multicast addresses. We could do broadcast, but it's the standards say to do, you don't do that, you do multicast addresses, and we've seen that they are derived mechanically from the IP multicast address. This we've discussed last week, and we've discussed also that multicast is either sent as broadcast or as multicast in the switches. How can a smart switch know, for example, that if only B and C are listening, it should send it to B and C and not to D? Well, there is no clean way to do it. The only way to do it is to look at the IGMP or MLD join messages, which in principle a switch should never do, because a switch is a layer 2 device. So a switch, as we have discussed already, if it wants to do this, it needs to be informed of who is listening to. So it will listen to some packets, which are those IGMP packets. And if there is more than one switch, it will do the same as what routers do. It will send this packet further to other switches using the switch equivalent of PIM for building its own tree. A consequence of this is that routers need to have several forwarding tables. And we will see that they have even more than those two. They need to have one for unicast, one for multicast. If you do an ifconfig in your machine, you will see all those in the same table. So they can be displayed in the same, but they are handled differently because the unicast forwarding table follows the longest prefix match rule, whereas the multicast forwarding table follows the exact prefix match. So M1 is an address, not a prefix. And for every packet that receives with a given address, you have to go to the table. And in principle, you should find only one table with one address. Whereas, of course, you can have several entries with different prefixes that both match the same address, in which case we take the longest prefix match. What is a consequence of this? The lack of aggregation. If the main idea of unicast addresses is to have a structure in the addresses such that all packets that go to EPFL, for example, have the same prefix. In IPv6, all packets that go to any Swiss university have the same prefix, so that the tables are small for all routers that are in the backbone in the internet. For multicast, it's impossible to aggregate because those are logical addresses. For example, here, if there is a listener to M1 and M2 and here a listener to M2 only, then the router like R3 will need to have two entries, but router R1 is unable to aggregate M1 and M2 into a single a single prefix. First, because the address space is not structured for multicast, and second, even if it would be, it would not make any sense, because who is listening to M1 and M2 can vary over time. So this can change always, so it's very difficult to aggregate, and in practice it's not done. So there is a high price to support multicast. This is why multicast it suffers for the per flow state in routers and is not deployed in the global internet. So if you do a Balelec thing here and you want to stream it over the internet using multicast, it won't work. You will not be able to stream it to the entire world. You will be able to stream it to the EPFL network. ISPs, telecom companies, use their own multicast, but they don't open it to everyone. And there are several reasons. One is the scalability problem. Another one is multicast is, of course, more susceptible to attacks, because if you manage to send a packet to a group that covers the whole internet, then you have considerably more power. So it's more difficult to secure and to monitor in case of denial of service attacks. Those are some of the reasons for multicast not to be deployed globally. But it's very much deployed in lots of particular cases, so we will use it in the lab. Multicast doesn't work with TCP. We would love to have it work with TCP, but it's very hard to do, and in practice, impossible. Why is that? It would be nice if I send a video that I'm sure if a packet is lost, it's retransmitted automatically. Yes?
Because TCP enforces the order of the packet received.
TCP enforces the order of the packets received. Yes, but that's not the main reason. Yes?
Different clients or destinations might be under different network conditions. So your packets for a transmission might vary differently in different parts of the nation.
So different destinations might be in different conditions. That's true. But imagine you do TCP for multicast. Imagine a second you do it. Can you see a problem? Well, TCP uses acknowledgements. So, of course, if you have two destinations, you could say, okay, I have two acknowledgements, and I need to keep an acknowledgement for each of the destinations. But if you send TV and you have, like Swisscom, perhaps 1 million people following a football match, you will need for each of the 1 million destinations to keep all those resequencing buffer and all that stuff, and all the windows, etc. So it will very quickly blow up. So TCP keeps state information on a pair per pair of source and destination. The idea of multicast is that you don't want to do this. You don't want that the source has to keep state information for all the destinations. So in practice, TCP does not work. There is no implementation of TCP that I've seen that has been adapted to multicast, because there's a fundamental problem. There are application layer equivalents of TCP that do it for multicast, but they try to do it smartly, in a smarter way than TCP does it, by using parities instead of retransmission. The idea is if you send a packet to 1 million destinations, for TV you probably don't care if it's online TV, real-time TV. If a packet is lost, you don't retransmit it. For example, digital TV. I mean, if you use TV over the standard TV channels, not over the internet, this is digital, so it's sent in the form of packets. But there is no feedback from the source, from your TV set. It's not speaking to the source. How are errors controlled in such cases? Well, one could say there's no error, but it's not true. Once there's always errors in any wireless transmission mechanism. We use here forward error correction. So we add, if you have to send 10 blocks of data, you send, for example, 2 additional blocks using Reed-Solomon code, for example, such that if any of the 12 blocks, that any 10 of the 12 are received, then you're able to reconstruct the 10 blocks. And if once in a while you receive not 10 but 9 because 3 are lost or corrupted, then you will see a problem, which you do on digital TV. You see once in a while you have big squares that are showing errors. This is the way it works. So you can use similar methods if you use IP multicast by requiring from the sources to have some feedback once in a while. And if somebody has some missing data, you can retransmit forward error correction data that will be able to correct several errors. So if one source has missed packet 1, one destination has missed packet 1, another destination has missed packet 10, by sending a parity with using Reed-Solomon codes, for example, you can have both corrections done in one packet. So those are the ideas that are developed for the replacement of TCP in multicast. But this is not very much used because most multicast applications have a streaming nature where the idea is we send the data, and if something is missing, we will very quickly resend something else that's able to correct it. But in some cases, for example, if we do software distribution over satellite links, you will use systems of that kind. But multicast is not only bad, it's very good. It's good for someone. It's good for the sources. If you're a source of data, using multicast is very convenient. Why? Well, first, if you have 1 million receivers, you send only one packet for 1 million. So that is very easy. So that's very well adapted, for example, for TV distribution. If you send exactly the same channel, live TV, for example, then it's much better to do this. Now you could tell me, but somebody is replicating the packets. It's the routers. So if somebody is replicating the packets, there's no benefit. Yes, it's not the source that creates 1 million packets for 1 million receivers, but it's the routers who do it. But still, there is a difference, because if I have, for example, a chain of routers, say I have 10 routers that each duplicates the packets, after 10 duplications, I have created 2 to the power 10 packets, which is 1,000 packets. And after 20 duplications, so you have 20 routers in the path, by having every router simply duplicate a packet, which is not a very difficult job. You receive 1 packet and you send 2, not 1 million. Then at the end, we have 1 million packets. So by the fact, this exponential law, that if you have a network, the larger the network is, the more there is possibilities to multiply the packets, and you can reach a very large number without having anybody creating a large number of duplications. That's the main idea of multicast. Another interest of multicast is if you have sensors or relatively dumb devices that you don't want to bother having to say with whom they're talking. For example, if you have a sensor that reads temperature measurements and you have several data sinks that want to receive that data, then you don't want that, and if it's in the open, for example, you don't necessarily want that you have to log on to the sensor to establish a session like you would do with unicast. You can simply have the sensor send, and whoever wants to receive will receive. So you can have, in particular, several servers that will receive the data. Voila, that's all we will see about multicast, except for this little quiz now. Yes. Here I'm proposing 3 statements, A, B, C. Which ones are true? I close in a few seconds. Wow. So Dirac on answer B and C, 1, 2, 3, 4, 5, 6, yes. Which of course is the only correct answer. Any other questions on multicast? Then we move on to the next topic, which is routing.